Welcome to Networks Professionals.
Hey everyone, and welcome back to The Explainer. So if you've ever spent any time dealing with enterprise networking, you know the drill. Keeping everything running smoothly, it kind of feels like trying to conduct this massive chaotic symphony where, honestly, half the musicians are playing a totally different song. Well, today we're zeroing in on the absolute foundational heartbeat of those networks, OSPF. We're going to break down exactly how it organizes network architecture and then look at how these routers actually establish their relationships.
All right, here's our roadmap for today. First up, we'll look at scaling the OSPF network. Then, containing the blast radius. Number 3, establishing router adjacency. And finally, we'll wrap up with the 7 strict OSPF states. Let's dive right in.
Section 1. Scaling the OSPF network. The macro view. So, picture this. You've got this completely chaotic, overloaded network environment, right? Devices are just being added left and right, and it desperately needs some kind of organization before the hardware just straight up collapses. In a single area network, every single router has to mathematically recalculate the shortest path tree whenever any link changes anywhere. Literally every router is constantly processing everything, and that causes massive CPU.
Now, before we go any further, we really need to clearly define what exactly is being updated during all those constant recalculations. We're talking about the LSDB, or Link State Database. Basically, this is a highly detailed, perfectly identical map of the network topology, and it's maintained by every single router. Getting a handle on this database is absolutely crucial if you want to understand why an overloaded network ends up crashing. See, if the network is just one massive area, every router has to hold that entire gigantic map in its memory and update it constantly, which, as you can probably guess, is exactly what we want to avoid.
Moving on to Section 2, containing the blast radius, limiting the damage. Think about a massive single-area network like a room packed wall-to-wall with explosives. No joke. Just one single flapping link can spark this network-wide recalculation that ripples across every single device. It's a nightmare. So, OSPF Areas step in to act as protective blast walls inside that room, and they deliver 4 massive benefits. First off, they drastically reduce the LSDB size. Second, they limit that blast radius, so if a link flaps over in Area 1, it absolutely doesn't ripple over into Area 2. Third, they create this really clean hierarchy, all anchored by Area 0, the backbone, which prevents those dreaded routing loops. And finally, they reduce overhead by using stub areas to limit exactly which routing updates are even accepted.
Section 3. Establishing router adjacency. The micro view.
Okay, let's zoom way in from that massive macro architecture. Let's peer closely at how 2 individual routers actually meet face-to-face. Because at the end of the day, those huge areas are built one single connection at a time. I want you to think of neighbor adjacency as this high-stakes professional networking event. These individual citizen routers have to properly introduce themselves before they even think about exchanging sensitive data. And they do this using hello packets. It's how they discover each other, negotiate their parameters, and ultimately synchronize those link state databases we talked about earlier.
Which brings us to Section 4, the 7 OSPF states, the handshake protocol.
So, before these routers can ever exchange vital routing data, they've got to progress through a really strict 7-step social sequence. Phase 1? That's all about discovery. Routers start off in what's called the down state. This is when no hello packets have been received yet. The router is out there actively multicasting hellos out onto the network, basically blindly shouting into a crowded room, just hoping to find other devices. Then we hit the init state. That's when a hello actually gets received. And finally, in the two-way state, bidirectional communication is confirmed, and if they're on a broadcast network, they'll go ahead and elect a designated router.
You know, I absolutely love this analogy for the init state. It says it's like waving back at someone who was actually waving to the person behind you, right? It perfectly captures that incredibly awkward moment in network communication. The router receives a hello packet, gets all excited, but then it realizes its own router ID isn't even listed in the packet yet. It knows someone's out there, but it just hasn't officially been recognized by name yet. Talk about awkward.
But hey, once they get past those awkward introductions, they move right into Phase 2, which is synchronization. In the X-start state, they establish a clear master-slave dynamic. The device with the higher router ID takes charge. It becomes the master to sequence the whole data exchange. Then comes the exchange state. This is where they swap database description packets. You can think of these as basically tables of contents for their databases. Next up is the loading state, where routers use link state requests and updates to actually fetch the full details of anything they realized they were missing. And finally, the holy grail. They reach the full state. Adjacency is officially achieved, and those LSDBs are perfectly, completely synchronized. Just look at how beautifully logical the business end of this relationship is. Exchanging your business cards, or those tables of contents, that happens in the exchange state. Demanding the missing files that you noticed from looking at that table of contents, that goes down in the loading state. And once you finally have everything, you hit perfect synchronization in the full state. It's only at this exact point that the router can finally run its shortest path first algorithm to calculate the absolute best routes.
But as we wrap up this explainer, I want to leave you with a real-world scenario to chew on. What actually happens if your routers get stuck before reaching that critical full state? Like, if you're stuck in X start or exchange, could something as simple as mismatched maximum transmission units or maybe misaligned hello timers be quietly sabotaging your adjacency? Troubleshooting these stuck states, that's a massive chunk of real-world network engineering. It just goes to show that knowing the exact steps of the structural handshake isn't just some textbook theory, it's literally your ultimate diagnostic tool. So I highly recommend diving deeper into your own network configs to see if your timers are truly aligned. Thanks so much for hanging out with me on this explainer, and I'll catch you in the next one.
Thanks for watching.